So understanding how long viruses remain infectious in the air is important because it allows us to estimate the risk of transmission. Now, I would argue that it's actually more important to understand why viruses lose infectivity in the air. Because if you can understand that, you can design more effective mitigation strategies by essentially maximizing the natural way in which viruses lose infectivity. Now, in order to do this, you have to study viruses while they're airborne, and this is not easy. So in the course of this video, I'm going to discuss the many ways people have developed over the years to study airborne viruses and really dig into some of the underlying challenges involved in these studies.
First, some context. When you want to study how long any organism remains viable in a given environment, there's a lot that you need to consider. For example, let's say you want to study what affects how long a shark can live in the ocean. Well, you can't exactly build an ocean in your lab, and you can't monitor everything that a shark is exposed to over its entire lifetime in the ocean. Meaning, to study this, you need to conduct your experiment where you control as many of the countless parameters that affect shark health as possible. And since you can't do this, this means any experiment on the lifetime of a living organism is going to be on a spectrum, where the system you're studying is somewhere between exactly accurate and not accurate. And this is fine. The most accurate case would be the shark in the ocean. But as mentioned, this is impossible. The least accurate would be something like, a shark on a picnic table. Again, this is not to say that experiments done here are good and those experiments done here are bad, but rather all of these experiments are useful regardless of the environment probed, as you will all learn something in every experiment. The key is that you fully appreciate where you are on the spectrum in both the design of your experiment and critically the interpretation of your results. For example, if I put a shark on a picnic table and measured the lifetime, the results would be minutes. Now, my conclusion should not be that sharks live for minutes in the ocean, but rather my conclusion should be that the water seems to be very important for shark survival. Now, if I were to increase the complexity and put the shark into an aquarium, I would find that the survival time would be highly dependent on what's in the water. Salt, for example. Again, what is learned and the implication of the measurements will depend entirely upon my recognition of where I am on the spectrum. Often, when scientific studies are reported in the media, both mainstream and social, where the study is on the spectrum is often not fully appreciated. Typically, the authors of the paper will correctly identify its location on the spectrum, but sometimes the reporting of the paper will describe the findings as though the experiments were done, say, over here. Now, obviously, this will lead to a lot of confusion, and this confusion can be made worse if new studies come out that report seemingly different results. Now, often these studies are contradictory to only those unfamiliar with what's actually being measured. In short, the interpretation of any study on how long an organism remains viable will be highly dependent on both the experimental techniques used and the environment in which the conditions were probed.
All right, so since we're talking about airborne viruses, what environmental conditions should be probed? Well, since viruses are carried on exhaled aerosol, it's critically important to understand what happens inside an exhaled aerosol.
When exhaled, the aerosol that contains the virus will begin to change rapidly, leading to many changes within the aerosol. For example, water will quickly evaporate, causing the concentration of all the sugars, salts, and proteins and mucus that make up the aerosol to increase significantly. The concentration can reach supersaturation levels, meaning that the concentration of the chemicals in the aerosol cannot be reached in the bulk phase, so things like in a bottle. The time taken for this change in concentration can be very rapid, on the order of milliseconds to seconds, and if the concentration gets high enough, this can lead to the salts crystallizing out of the solution. The reduction in droplet size will result in the higher surface to volume ratio, meaning that the likelihood of the virus interacting with the unique microenvironment that is the surface of an aerosol will increase. Respiratory aerosol will also lose CO2, leading to a large increase in pH. I discussed this in greater detail in a previous video. I've put a link into the description. So it's not only the initial composition of an aerosol that determines how long the virus will survive, but also how the aerosol physically and chemically changes in the air will also play a critical role.
So many conditions in an aerosol can only be reached in an aerosol. Like for example, sodium chloride can't get super saturated in the glass, whereas it gets super saturated in the aerosol phase. So ideally, to study airborne viruses, you ought to study viruses well in the air. Okay, well, how do people do this? Well, there's a number of ways that have been developed, and I think the best way to walk through this is going through increasing complexity.
The simplest way to measure airborne viral decay is to estimate the conditions in the droplet and then simply make a bulk solution that has the same conditions, and then measure the viral decay in that. And much like the shark on the picnic table, you're able to find some information out, even though the conditions are largely not similar to what the virus experiences in the aerosol. For example, the large volume ensures that the conditions in the system are static, meaning that the virus won't experience the same complex chemical aging that a virus will experience in the air. Shown here are just some of the positives and negatives of using a bulk sample to measure the viral decay. Now, to address some of these limitations, such as the low surface to volume ratio in the bulk, another approach is to place a very small droplet, typically something like a microliter, onto a surface and see how the virus decays within that solution. Something that happens in the large droplet that doesn't happen in the bulk is that the droplet will evaporate, and the concentration of the solutes can get very high and may even change phase. This provides further insights into viral decay. Now, notably, this method very accurately mimics what happens to a virus during fomite transmission. So shown here is a summary of the advantages and disadvantages of this approach. Now, since the presence of the surface may affect things within the droplet, people have developed ways to levitate large droplets using acoustic levitation, literally levitating a droplet using sound waves. Very cool stuff. And now with this technique, sound vibrations are used to suspend a microliter-sized droplet in the air, and how both the conditions of the droplet change and viral infectivity change over time are both readily probed. Now shown here is a summary of the advantages and disadvantages of this technique. With both the droplet on the surface technique and acoustic levitation, researchers can study the effect that environmental conditions such as temperature, humidity, and the composition of the air will have on viral decay. Collectively, by probing larger systems, the researchers will have a high degree of control over what the virus is being exposed to, as well as a very good control over the timescales being probed. Also, by using a larger volume, there's more physical virus available to probe how the virus decays using various microbiological assays.
So a lot can be learned from these bulk large droplet type measurements. Now, in order to get a better and a full picture of why viruses lose infectivity in the aerosol phase, these bulk measurement findings ought to be coupled with measurements made on very small, tiny aerosol.
So, how small are we talking about? Well, since we're interested in aerosol that is exhaled, the diameter of the aerosol we need to study is under 10 microns, which is less than the width of a human hair. Now, for comparison, the microliter droplet that was used in the acoustic levitator is almost 2 million times larger in volume than an exhaled aerosol. To study aerosol this small, researchers often will use a nebulizer as their source, as this will produce a population of droplets that are similar to an exhaled aerosol in size. There are many types of aerosol generators available. Now, for safety reasons, obviously researchers can't simply spray infectious aerosol into a room. Thus, people have come up with many ways to confine aerosol in a space where it can be exposed to controlled conditions. Some have used chambers to hold the aerosol. A limitation of this approach is that the aerosol will settle out of the air, which will affect how the decay rate appears. Now, what I mean by this is that only the airborne virus is sampled. So if the aerosol falls out of the air, it can no longer be sampled. Thus, the recorded decay rate in these techniques is actually a combination of both the sedimentation rate plus the loss of infectivity. To address the sedimentation issue, a very common approach is to use a large rotating drum. The draft produced by the rotating drum helps to keep the aerosol suspended in the air, which reduces the effect of sedimentation. Another way in which people trap the aerosol is with spider webs. Literally. They then expose the web-trapped aerosol to whatever conditions they're interested in. With this approach, there is no sedimentation loss. This is very cool stuff. I've posted a link in the description to a DSTL video where they show you how they do this. So, in terms of the spectrum I talked about earlier, these techniques will be closer to this end, where the environment the virus experiences is very similar to the real world experience. So, clearly there are advantages to using small aerosol to study airborne viral decay. However, like large droplet and bulk studies, there are some limitations to these approaches that I think are important to consider when interpreting the data. Now, when you compare the advantages and disadvantages of the small aerosol studies with the large droplet techniques, you'll see that they actually are quite different. Moreover, often the negatives in one approach is the positive in the other, which is an opportunity because we can use the advantages of one technique to offset the disadvantages of another. What this says to me is that to truly understand how and why viruses lose infectivity in aerosol, we should use a combination of these different techniques.
So, like, while asking why viruses lose infectivity in the air may seem like a straightforward or simple question to ask, it's actually a very difficult question to answer. And the reason for this is to answer it, you need to have expertise in virology, chemistry, aerosol science, have some engineering involved. And you need to couple this expertise with a range of robust tools to make these measurements, to be able to study this process from various different angles. And it's really only through this combination of expertise and technology that we can really address and answer these very complicated questions. In future videos, I'm going to start presenting some of the technologies we've developed in Bristol to study this process. I think if you found this video interesting, you'll probably find those videos interesting as well. So with that, if you found this video interesting, please like. If you found it useful and you want to see more, please subscribe. If you have any questions, ask me on Blue Sky or Twitter or in the comments below. And with that, yeah, Mix has all the references that I used to make this video. Thanks.